lecture. Okay, so this is the first lecture for class one, day one, right? And machine learning for music and audio. I'll try to maximize the screen to see if, yeah, so we get a better quality of the video recording. Okay, sorry about that. If I don't find the audio, let's forget about this. Okay. So machine learning for music and audio. I'm Shlomo, and you have my email. This is the class, and in the previous video, we kind of went through the syllabus. So I'll jump into the contents of class one. So today we'll be talking about representation of sound in music, basically using either audio or MIDI. And MIDI, I'll put it in a second. We'll talk about musical features, or basically the basic constructs of music, which are notes, chords, melodies, rhythm. So this is kind of your musical introduction day. But also we'll talk about audio features. So if you think about this as ways of mixing and blending symbolic music and actual recording of music, or performance of music, we'll kind of try to give a broad overview and also point you to some toolboxes already that do stuff like that. So this first video is about representation of sound in music, data, which is MIDI and audio. So what is music representation? Basically, we have different ways of capturing, representing, storing, recording musical data. For those who studied music, maybe you're familiar with this way of graphical notation that tells you something about which note we want to play, how long this note is going to be, and some convention of how you read these notes. So there are these keys. So we'll talk about them. This representation, frankly, is meant as a set of performance instructions. So a pianist goes to a piano. So we have, I hope you can see my mouse, goes to the piano, takes this sheet music, and then he knows where to look up the note that he wants to play. So there is this aspect of an instrument that has to take this and render this into an acoustic signal. So what we see here in a blue graph are actually representation of vibrations in the air that become, what we hear. So to understand, the conventions of what musical signals are, we'll refer to traditional sheet music representation. And I'm partially reusing slides from Miller's book, Müller. We have a link on the website. Thinking about music in this way as set of instructions of playing notes is in some sense limiting, but on the other hand, I think it's important to understand that music is a very limited set of audio possibilities, or at least there is a big debate in music, why we choose notes and not noises. And today we do use a lot of noises in music. So, if you come and study composition, I'm sure you'll be exposed to these dilemmas of what actually makes a musical sound. But our basic assumption is that from all possible sounds, right, and we have, car crash noises, right? You have rain, you have engines, you have speech, you have animal vocalizations. We actually limited the scope of sounds to a very specific set of tones, which were artificially produced. So in that sense, music is a little bit unique, that we're trying to model a very small subset of possible sounds. And not only that these sounds have pitches, and pitch means that it has some kind of a, maybe I'll switch back and forth with some examples later, but they have so-called specific height that we perceive. So da 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 da. So it has very specific type of pitch, and we select only few of them and we map them to keyboard. So the notations are either graphical notations. So if you open up a MIDI file in some kind of graphical notation software, you'll be able to see them this way. There are these staves. This would be basically this note, which is also called by letters. If you use the American notation C, D, E, F, G, A. For some reason, A starts here in the middle. Most people know to recognize the C, which is how you would play a scale on the white keys. So you have a total of 7 white keys until it repeats. Or if you include these 5 black ones, we have 12 notes. And this idea will be following us for most of the musical data that we are going to encounter, because a lot of this is kind of a Western music notation that deliberately limits the selection of notes and frequencies to 12 possible frequencies, when the difference between that C3 and C4 will be so-called an octave. The frequency doubles. So this is really kind of a crash introduction. Those who know this maybe are so familiar with this that it looks trivial, but those who never studied kind of the acoustic aspect of music theory, or never looked at or never studied music, that might be very novel. So we will show in a second how these notes, or how these letters with this number, so this number actually switches every time we hit this note. So kind of the way to recognize this, you remember this 2 and 3. So if you have this little pattern here, the one to the left, that's the C, and then it repeats, and it'll repeat again. So if I don't know if I'm moving the window from Zoom, but you see that's a C3, this is C4, this is C5. They keep repeating. You have this pattern of notes, which actually takes a frequency. Each one will have a different frequency. And this frequency will be doubling, and we subdivide this into 12 steps. From basic computer science perspective, you can say, just think about this as a representation. This is the representation. Usually we'll actually have something which looks like letters, and you have these little, this is called the flat, this is sharp. If we want to use ASCII coding, usually we'll use a small b here, and we'll still have a sharp here to represent these changes. So if we go from C to C sharp, we go 1 step up. If we go from D step down, that's a flat. These are 12 notes, and then these 12 notes reoccur. So here you have them in musical notation, right? This is this first octave, or the third octave, going from this note. So this is this, and this is this, and this is this. Now it repeats again. It will keep repeating. So in some sense, we're working with an alphabet. Okay, we're working with a set of discrete symbols that have this interesting repetitive structure, that they have some kind of an index that indicates an overall scope of these 12 notes. And then these 12 notes appear with a slight difference. And for those who are kind of confused what they are, I hope by the end of the lecture it will make more sense. But this is the keyboard. So given that, we also want to mention that notes are written with different durations. So if you see these little notations, and in music notation, it's easier to show it this way. Once we talk about MIDI representation, we'll show exactly what it means. But this is a traditional musical notation. You have note heads that you put somewhere on the stave. So when you move up or down, that changes the note that you play on the keyboard. But then there needs to be some kind of a reference beat. And then once you do this reference beat, usually it's, when you use quarter notes, this one as a reference, this would be 4 quarter notes. This is 2 quarter notes. This is 1 quarter note. And why this is the convention, I mean, I think that's not very relevant at this point, but a whole note is subdivided into a half note and the quarter note, and then you can keep subdividing into 8 notes and 16 notes. It's just that it's very hard to count on whole notes. You usually do 1, 2, 3, 4, 1, 2, 3, 4. If that's, if your rhythm is 4/4. And this will be, the duration of the 4 will be a whole note, or these will be half notes, quarter notes, 16 notes. And for you, I mean, kind of as the basic concept, just remember that we need to represent the pitch, which means which note we're playing, like we did here, which of the keys is pressed, and then for how long it's pressed. And if you don't hold the key, but you want to wait, you have a pause, you have a silence for some time, this is the equivalent representation. I don't expect you to be able to read musical notation if you haven't, if you haven't practiced that. It takes a long time. But just be aware that this is what, what the traditional music representation is. And a lot of musical software go back and forth. They can go between MIDI files and these notations. There is a separate, different task that we will not be talking about, which is how you take a recording, basically an audio signal, and find the notes. That's the transcription problem. And you can think about this as, a very practical thing, right? You want to find chords of a song. You want to be able to somehow analyze and understand a recording, maybe play with that recording. So in some sense, this representation, the notation, is a way of capturing kind of the meaning of music, or sound encodes these things. So going a little bit into how the computer would represent symbolic music, if this is the notation that you would use, the musical notation, and what we have is here, ta 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 ta. Okay, it's an opening of a very famous piece. If we want to represent this in a computer, basically this is the core of MIDI, and MIDI stands for music instruments digital interface. It was actually created as a communication standard to be able to trigger sounds from a remote synthesizer. So if you have a keyboard that doesn't have a sound and you press a key, and then you want it to play a note somewhere on a sound module, you will send a message. So these were basically messages that will turn notes on or turn notes off. They have 16 channel in principle. So if you have one of these instruments played by a different sound, different instrument, you would put them usually on different channel. And the notes are represented as numbers. So the convention is that that middle C, which is usually kind of our point of reference, this middle C here. Many times people kind of use this as a reference. They can also use the A, but kind of the octave numbers change on C's. So let's keep this middle C. It's usually given a number 60 in MIDI communication format. So this note here, G, is if you count the half steps, where you go and follow that keyboard and go from here to here, this is the G, this is this one. So this is the G, this one, and this one is a reference of 60. So 61, 2, 3, 4, 5, 6, 7. This is the note that we land on. So this note, if you kind of visually memorize, you remember that's the second on this stave, right? We have this key, and on the second line here, you have this note. This is the note that we see here, okay? This note here is translated to number 67. This one will be 12 notes under this, lower, okay? So if you subtract 12 from this 67, you'll end up into this note. Again, you have to read music notation or be familiar with this to immediately know that this is also a G, just an octave lower, and this is also G, 2 octaves lower. But it's easy to count it here. 67 minus 12, you have 55. 55 minus 12, you get 43. So these three notes, okay, I don't know if, I hope you can see the mouse, okay, maybe I'll connect a letter tape tablet to actually to leave a trace. But these three notes played at some time here, tick 60. So why doesn't it start at 0? Because we had some rest, okay, we had some silence here, okay. And depending on the tempo, so there needs to be some agreement of how fast these ticks pass, okay? And that's another issue that is important in trying to understand what musical notation is. But there was nothing happened for 60 ticks, and then this note happens, okay? And all of these notes are the same duration, Okay, so that should be also held for 60 ticks. Now let's look for a second at the representation on the right, which maybe is more better understood as mapping pitches to, or these like computer codes, right, to graphical representation. This is so-called the piano roll. Okay, you think about this as piano ticks, and this is the note being played. This is the 67 or the G4. This is the 55 G3. This is the 53 G2. The thing is that we stop a note and we re-trigger this because this is da 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 ba. So there's 1, 2, 3, and another note. So there is a little silence. In this way, the way this one was recorded, and this is not really specified exactly in the score. How do you make the transition? But here, it actually took 5 ticks as a note off. There was a silence. Okay, so this little gap here, hopefully you see it, is actually the note off of all these 3 notes. And then we kind of repeat and go on. So, just consult the slide and see what, go through the details. But this is the exact representation of this, which is exactly represented here, with a little caveat that there's a little bit extra. These little gaps are not exactly shown here. So this is kind of the performance of this notation, which is encoded this way. Now, what happens on the piano? So here, basically, when we play these notes, we have these little mallets that hit the strings. So here you have strings. You press mechanically a button or a key. Sorry, a button would be on a synthesizer. You press a key. You actually have a hammer that swings and hit the string. So these are strings, okay? And that string starts vibrating, and that's what creates the note. And these strings are actually tuned according to some convention. And this is how we relate the frequency of every string to a key. Because frankly, this kind of shows us this kind of a separation between this symbolic notation. So imagine here you had your sheet music, and somebody reads it, and then he presses the keys. These keys hit the strings, and these strings actually make the sound. And there are so many conventions here. We think this is maybe take it as a natural thing because we're so used to music. But somebody had to decide about the layout here. Somebody had to decide about the frequency, the tuning. Okay, so a lot of this really limits the type of sounds that we're going to deal with. Now, talking about symbolic representation as mechanistic one, if this is the piano we've seen before, you can actually run the keys. Here we have, the keyboard is closed, shut, because we have this little piano roll, which is a perforated paper that you could load in these pianolas, and they would run, and they will actually run the keys and perform music. So this is our piano roll representation, and this is the name where it comes from. It's actually a roll, a paper roll with punched, it's like a punched card. So for those who at least heard about, the old computer code that was using punch cards, like the PDPs and stuff, this is before that. You can think about this as programming a player to perform a sequence of key notes, key strikes, written as a piano roll. So this is kind of a quick summary of MIDI representation. We have MIDI note numbers, the pitches. They correspond to the piano keys. 69 is an A. We said 60 is a C. If you calculate 9 steps up, there'll be 69 concert pitched A4. Why it's mentioned specifically? Because this is usually a reference. You tune according to a specific convention of what this note, what frequency it should generate. There's aspects of how hard you hit the key. It's called velocity, just because in synthesizers that kind of translates to, the speed of your finger coming down, and that translates to how loud you play. A MIDI channel is usually tuned to be an instrument, so we'll see in a second that it doesn't have to be piano, it could be any instrument. You have note on and note off events, so the onset times, or silences and their durations. Is measured in some ticks or clock pulses, and let me move this button. Okay, and then you need to have some kind of reference tempo, saying how fast your clock moves. So this is a tempo. Okay, so I just I want you to be aware of this notion of speed, basically, because the same piece can be played slowly or faster. All right, now we move actually to the idea that this sound or these instructions of performance are captured in a sound. So if we have a tuning fork, which is maybe the most ideal sound source, when it vibrates, it basically pushes the air back and forth. So here it compresses the air, and then when it moves back, it kind of allows the airwaves to go farther apart, and then it compresses them again. These are actually air molecules, if you want, and they change this the pressure, which creates so-called longitudinal wave. So this is a wave, but it's a wave of pressure that moves from this fork that resonates or vibrates, okay, and creates a tone into a microphone. So in the microphone, there is a little membrane here that actually captures these changes in pressure and moves back and forth. And depending on the style, the type of microphone, whether it's dynamic microphone or the way it actually or piezo. I mean, there are a lot of mechanisms here that can take these vibrations and translate into electrical signals. Now, once you translate into electrical signals, that becomes the signal. So the idea here is that this actually electrical signal that comes out of the microphone represents changes in pressure. We think about them as waves or waveforms, and this is the electrical representation basically of changes in pressure. So once you understand that relation, the transduction process and capturing process, we'll abandon this idea and just think about waveforms. So waveform basically shows us how pressure goes up and down over time. And this is time, okay? And this is the change in air pressure. Now, we saw an ideal signal before, and this ideal signal is called sine wave. Why sine wave? Because actually sine, the function, the trigonometric function of sine wave looks like this. But you can have vibrations which are not ideal, and they might have multiple vibrations. So if body resonates with multiple frequencies, if they sum up, they create a pretty intricate waveform. And we'll kind of go back and forth when we talk about signals, trying to understand that once you do like a Fourier analysis, a frequency analysis, you actually take a waveform, which is pretty complex, and decompose it into these pure sine waves. And this will be the nature of our Fourier analysis. So it's kind of like, acoustics and signal processing on in a slide. So making this a little bit more real, if we have a note, so this is a waveform of a note that's being struck, probably piano, because it has a sharp attack and then kind of decays, and boom. And this is the waveform. This is how the pressure changed over time, or the electrical signal that was captured by a microphone. Once we start trying to analyze this into the constituent frequencies, okay, we might have multiple frequencies. So when we do frequency analysis, and I'm showing this just because we need a terminology. Okay, we'll talk about Fourier transforms, I promised, tomorrow or the day after. But this is basically the magnitude, and this is the frequency. So the important thing is to notice this is time. So this is how the waveform happened in time. Now we take all of that, we take this whole thing, and we try to decompose this into frequencies, or maybe we take a snapshot. So here actually we take just a snapshot of 10 milliseconds. And so we just take a small snapshot here. We look at the waveform and we decompose it into these sinusoids. And we can see that some match better, some match worse, but eventually, that's what the frequency analysis will allow us, is to find the strongest components that actually, if we combine them back, we'll get back something like the original waveform. So if Fourier analysis does the analysis for you, this is, if you want, synthesis, and we can talk about sinusoidal synthesis or analysis and synthesis, where you can either take sinusoids and add them together with different amplitudes to get, a specific sound color or timbre, and I'll go back to the notion of timbre in a second. Or you can take a sound and you can decompose this and find how strong should be the frequencies and what are the frequencies that if we add them together, we'll get this note. So now, when we think about the process of moving from symbolic notation into waveforms, so we had a piano in between here, and now we take this and we analyze this in a computer by decomposing this into frequencies. You can see that a specific and a very peculiar aspect, which is interesting, also to speech and to music, is that these notes, okay, which have a specific pitch, or they have this notion that we hear them as higher or lower notes, da, da, da. They also have multiple sinusoids. And these multiple sinusoids are very often spaced. If this is a really periodic sound, and we can actually show this mathematically, that if this is exactly periodic sound, if this is really period, you can actually say this repeats exactly and repeats exactly. Like here, these are like 3 exact repetitions, or 4, sorry, here, 4 exact repetitions here. If this is an exact repetition, then you need to have sinusoids, or the sinuses that can add together to create that sound will be always multiples of the lowest note. This is why they're called sometimes partials or harmonics. Harmonics in the sense that you have some fundamental frequency. The notion of fundamental frequency is important. And then you have these multiples of the fundamental frequencies, which are harmonics. In acoustics, we use a lot of terminology. You can call partials, but partials would be basically any sinusoidal component. Harmonics would be sinusoidal components, which are basically multiples of each other. So these notes, you see, as we go up on the musical scale, you can see, it's hard to see, but you can kind of, if you go from here to here, you can see that the fundamental frequency went up, and also all the other sinusoidal components spread out, because they are multiples of that basic frequency. So how we read this is frequency in hertz, and I'll talk about what the hertz are. Okay, these are basically periods per second. This is time, okay? And there is a gray coding here, which relates to how strong every component is. So here we have, in a nutshell, the Fourier transform. Now, I kind of said we're not going to talk about Fourier transform, but I think it's important because this is the representations that now we can look and have a computer take this recording, decompose it here, and maybe this, is a little bit closer to this, okay? Or maybe we can turn this into a MIDI file. While just looking into this, it's going to be very hard for us to tell what are the pitches. So in some sense, we want to go from recordings to frequency analysis, just because from this, we might go back and understand what was the initial musical content that generated these sounds. So if we put everything together, okay, you can have this piano roll, okay? And unfortunately, I think we didn't, no, okay, that was the missing file. I'll try to correct it later. But if you have this piano roll, which is one-to-one actually a MIDI file, okay? Because it tells you which notes, how, these are the different pitches, these are the different notes, okay? The size of the black square, or the black whatever, that segment is really how long this note is, okay? The one thing missing here is actually how loud you play these things. I mean, one of the issues with piano rolls is that it's very hard to control dynamics. In the MIDI file, we have this extra information that actually tells you also how strong every note is. But these are the notes. If these notes are performed, they create this acoustic signal. We take a small segment of this acoustic signal, we do frequency analysis and see which frequencies actually were existing in that moment. Now, because we have multiple notes here, we might have frequencies here which belong to multiple fundamentals. So if we take this analysis that we'll talk about much more in detail in the coming classes, this is so-called a spectral analysis. This is a spectrogram. You have time here, you have frequency here, okay? So if you run that file through a spectrogram, you'll get a picture that looks something like that. I mean, there are some parameters to tweak to get really the picture you want. But what I want to kind of relate is now this analysis to the original score. Okay, if you try to overlay them, and I did this manually, so this is not an exact, I didn't really try to detect the pitches, but it seems that these were the fundamentals. These were the notes that were being played. Everything above that were actually the overtones. These were the harmonics. This what created this, that what actually made it sound like a piano, whatever instrument is playing. This, in this case, it was rendered from a MIDI file using a synthesizer that was tuned, or actually the program, the channel was playing a piano sound, a piano synthesizer. That was not a physical piano roll piano, that was an electronic piano. But everything, we hear all of that, but these are the notes, and everything else here is actually the instrument. You can go and create very strange spectrogram analysis from sounds which are not harmonic. And when I said that we kind of limit ourselves to these nicely looking harmonic, or things that look like these lines, and maybe many of them together that start looking something like this, it definitely is different from trying to create a picture like this. So if you check out the FX Twins window licker, this is noise. I mean, they actually shape the noise in some way. I don't know if this is, there are lots of stories of why they did this and why they hide these images in, but even from the shape of it, this is not a musical example. Okay, so I think this kind of brings us, summary of this section. What we studied was MIDI representation that captures the notes, or the piano keyboard presses and releases. It corresponds to the lowest part of audio frequency spectrum, usually the lowest periodic component in the note spectrum. So if that looked totally confusing before, I hope now it makes sense. I mean, you didn't see this before, but if you have read this before going through all the explanations, I think it probably wouldn't have made much sense. The fundamental frequency is this lowest partial, which is the note you play, and then you have all the other frequencies that you look at, and it captures basically the notes. The audio recording captures the air vibrations as a waveform, and that waveform, of course, comprises of all the frequencies generated by that instrument, not just the fundamental. And then when we do the spectrogram analysis, and specifically we just look at the amplitudes of the sinusoids, or how strong they are, they show how the frequency contents in the recording change over time. So I'll stop the recording and sharing right now, and open this up to some questions, and let's see what time it is, and then move on to the next one.